All right. Okay. So, today we are going to cover unsupervised learning, and this covers clustering and other, other things in this umbrella of unsupervised learning. So far all of the methods we've learned have been supervised learning methods. And what that means is that we have target values. And what we are trying to do is we're trying to get our predictions to be as close as we can to our target values. So um, we, by having target values, we're able to calculate a loss function, okay, which measures, how different our predictions and the target values are. On the other hand, when we have unsupervised learning, we don't have target values. And instead, what we're doing is we're searching for, I don't know, for lack of a better word, structure within just kind of like the input values itself. So you basically just have an X matrix. You don't have Y labels or target values, and you're trying to find, some kind of structure or patterns within just the X. And so, broadly speaking, two of the biggest applications are clustering, which is trying to put similar observations together, and then dimension reduction, which will be, reducing, I guess, uh, the number of dimensions or if you have any kind of redundant predictor variables. And so we'll take a look at both of them. Today we'll look at clustering, and then in our next lecture we'll look at dimension reduction through principal components analysis. All right, so as far as clustering goes, the goal is to create groupings of objects that are similar so that objects within the group are more similar to each other and objects in different groups are not similar, right? And how do you define similarity is a good question. Okay, and there's lots of ways to define similarity. We're going to look at like some distance metrics. And, as far as applications of clustering goes, um, you know, every time you go shopping, whenever you click a product, there will be like other similar products. So that's all driven by clustering, grouping similar documents together, even like grouping physical locations together. If you ever use Uber or Lyft or something, you can get like a shared ride, and then they're basically trying to create similar, cluster different passengers together to share that. Okay. All right. So as far as k-means clustering goes, it defines similar objects as objects that are close to each other as far as Euclidean distance goes. Okay. And it is important that we don't mix up Euclidean distance. I'm sorry, don't mix up the k-means clustering algorithm with k nearest neighbors. They both have k, and they both, um, I don't know. Yeah, they both have k in there, but they're very different. So k-means is unsupervised. It's a clustering method. K nearest neighbors is supervised, and it is a classification method. K-means is iterative, and K nearest neighbors, there's no iterations. It just uh, does. Okay. Um, Clusters are going to be defined by the centroids, and the centroids is going to be the center or the mean of the points that are assigned to that cluster. So if you have cluster K, its centroid, and this is basically just a fancy formula that just says take the mean of the points assigned to that cluster. So you have Z, which is an indicator variable, and if observation N is in cluster K, then Z and K is going to be a 1. And if it's not in cluster K, it's a zero. So when you do the sum over n, the denominator will basically be how many points are in cluster K. And then the numerator, you'll have ones multiplied by the x's for which x belongs to K. So the numerator will be the sum of the x values in cluster K. So it's basically just take the mean of all of the points that belong to cluster K. But in formula, it looks like this. But there's a bunch of different ways you can do this. And with the computer, you could just, filter down or subset down to the observations that belong in cluster K. Or you can create a column, ZNK, ZK, which will have ones and zeros for whether an observation belongs in that cluster. And then you multiply and divide and so on. And so the way the clustering algorithm works kind of like this. And there's a couple initial starting methods regarding the clustering algorithm. And so here I'm going to use the random partition method, but you could do a different method where you just select arbitrary points to be your centroids or things like that. But anyway, um, the first thing is you have to decide how many clusters you want to search for. And then you're going to randomly uh, just assign the points to each of the clusters. So this is the random partition as you just, for every point in your data set, you just randomly assign it to one of the clusters. And then once all of the values have been assigned to a cluster, then you're going to say, okay, all of the points that belong to cluster one, what is the centroid of cluster one? And you calculate the centroid for each cluster. And you're going to do this for centroid 2 and centroid 3 and so on and so forth. And then once you're done with that, now that you have new centroid values, you're going to reassign the values to the clusters by associating values in the data set to the nearest centroid. And the nearest centroid will be the one that's nearest using Euclidean distance. And then you will just repeat this until you'll go back and forth between recalculating centroids and then reassigning points. Okay, recalculate centroids, reassign points, recalculate centroids, reassign points until you reach convergence. Okay, and convergence occurs when there's basically no reassignments. Okay, no points change cluster assignments. And, you know, which value is the nearest? We're using Euclidean distance. You could technically use other um, uh, distance metrics. I think there's k-medoids clustering, which doesn't calculate means, but uses, you know, like median points, medoids. So it's like a centroid, but the concept of a median, and then it would use Manhattan distance, uh, or absolute value distance, which works a little bit better with medians. But anyway, there's similar but slightly different clustering algorithms. Okay. The 4G method is an alternative initialization method. And rather than randomly assigning points to the different clusters, it just randomly selects K observations from the data set and uses those as the initial centroids. And then the algorithm proceeds where you reassign points to the clusters and then recalculate the centroids. So the random partition method tends to produce initial cluster means near the center of the data, while as the 4G method tries to spread them out. Okay. Now, because clusters are assigned using Euclidean distance, it's recommended to normalize or scale all of the variables so they are of similar magnitude. And that way, one variable that's, just measured on a different unit or something and is much bigger. Again, using height and weight as an example, if you use weight in pounds and height in inches as kind of your baseline values, then the weight variable will tend to kind of dominate just because its values are much bigger and there's a much bigger range for weight and things like that. So you normalize everything and then you get z-scores and um, and then you don't have as much of a problem there. Okay. Um, so yeah, if variables aren't normalized, then the variables with a much greater magnitude will just kind of have a bigger impact. So here's a toy example where I start off with 8 data points, and we are going to search for 2 clusters. Now, just visually looking at this, our brains can identify a cluster up here and a cluster down here, and we can see that very readily. But we will do we'll run through the algorithm and make sure that k-means clustering can identify the clusters, as we would anticipate. Okay, so we have 8 points. We got 0, 0, 1, comma 0, 0, comma 1, 1, comma 1, and then 3, comma 3, 4, comma 3, 3, comma 4, and 4, comma 4. Okay, so these are our points, and um, and so what we're going to do is we're going to search for 2 clusters. Okay, and um, and so here I'm going to just randomly assign points to a cluster. Sorry, I'm hearing some noise in my apartment. Um, and we're going to just randomly assign points to cluster one and cluster two. So I'm just going to just randomly sample one or two, okay? And make those clusters, and then I'll make a column of z's, which will be either zeros or ones, okay? Uh, we're going to take assignments equal to 1. If it's true, it's going to be a 1. If it's false, it's going to be 0. And so we'll get columns of z. And so when we do that, I happened to assign 5 of the points to cluster 2, shown in red, and then I have 3 of the points assigned to cluster 1, shown in black. Okay, so this point, this point, and this point are assigned to cluster 1, and these 5 points are assigned to cluster 2. So we'll run through this, okay? And so these 3 points are assigned to cluster 1, point 1, point 4, and point 8. And so you can see the Z1 column for which points are assigned to cluster 1. We have ones for point 1, point 4, and point 8, and zeros elsewhere. And basically, we would take the product between Z1 and X1, and we would get 0 plus 1 plus 4, okay? And then we would take the mean, divide by the sum of Z1. So looking at X1, we do 0 plus 1 plus 4. We get 5 divided by 3. We get 1.67. We do the same for X2 times Z1, and we get 0, you know, 0 plus 1 plus 4, and we also get 1.67. Doing the same thing for column cluster 2, we take the product of Z2 along with our X clusters. And so we'll have ones for points 2, 3, 5, 6, 7. So we get basically 0 plus 1 plus 3 plus 3 plus 4. And we divide that by 5 and we get 2.2. Same thing for column 2 and we get 2.2. So the mean of cluster 1, the centroid of cluster 1 is going to be 1.67 comma 1.67. And the centroid for cluster 2 is going to be 2.2 comma 2.2. So if I plot these, and I can also use just dplyr and just do a group by and say calculate the mean of each group, and that would also work. But if I plot these, the mean of cluster 1 is this, and the mean of cluster 2 is this, right? So if you look at cluster 1 shown in black, the centroid of those 3 points is right here. And if we look at the mean of cluster 2 shown in red, the centroid of those clusters is going to be right there. So then we reassign all of the points to the nearest cluster. So starting at kind of here are two points, and we say, okay, this point right here, measuring the distance to each centroid, which centroid is closer. So the centroid of cluster one is closer. So this point will get assigned to cluster one. So we'll color it in black to indicate that it was closer to centroid one. And then, we do the same for all of the points and we say, okay, which centroid is closer? We say the shorter Euclidean distance is this one. So we'll see that all four of these points will get assigned to cluster one in black. And then we do the same for all of these 4 points. And we can see for each of these points, centroid two in red is going to be closer. And so as we go through, after reassigning, these 4 points got assigned to centroid one because this was closer. These 4 points got assigned to centroid two because it was closer. And so this is what we get after reassignment. And then once we have these points, we're going to recalculate our centroids. So once you finish the reassignments, you recalculate your centroids. And so doing that, we say, hey, what is the centroid of these 4 points? And we would get 0.5 comma 0.5. What's the centroid of these points? And you'd get 3.5 comma 3.5. All right, and that's what we have right here. And so I can plot those new centroids, okay? And so here's the centroid of cluster one, centroid of cluster two. And then if we go through and we measure which centroid is closer, we would see that all of the points are already assigned to the centroid that is closest to it. And so there would be no reassignments, and we would say everything has converged. And so for our toy example, k-means clustering has correctly clustered our points into two clusters. Here is just another example. And so in this example, I created kind of 3 clouds of points using the multivariate normal distribution. And so I have, cluster one in the center in black, cluster two over here on the left in red, and cluster three over here in green on the right. And you can see, there's a little bit of scatter for each of these. And so this red dot from cluster two has kind of strayed into the territory that's kind of dominated by cluster one. And so, when we cluster these, this dot is probably going to end up getting classified as being belonging to the center cluster. Now, one thing is that when we do clustering, okay, the data comes in completely unlabeled, and we're just kind of looking for structure. And we might say we're going to look for 3 clusters, and it may or may not label the center cluster as cluster one, okay? Like if I have cluster A, B, and C, I say search for 3 clusters, cluster A, B, and C. The center cluster might be cluster A, it might be cluster B, it might be cluster C. So you will often have like different labels, right? So you might identify 3 clusters and you might identify them correctly, but what you call cluster one may not necessarily be what someone else calls cluster one or cluster A or cluster whatever. Okay. But that's okay. That's not an issue. But anyway, the data comes in unlabeled. And what we do is we just start off with random assignments. So we just randomly assign each point to belong to one of 3 clusters because we're going to say we're searching for 3 clusters. And so you can see some of the points got assigned to cluster one in black, some got assigned to cluster two in red, some got assigned to cluster three in green. And based on that, we're going to say, okay, look at all of these random assignments, take the means of each of these things. And so I had the computer calculate the means, and you can see they all kind of ended up very small, 0.08, 0.037, 0.259. This is just kind of by random assignment there. And so the 3 centroids get plotted in the center, and the way R plots dots is that it plots them on top of each other in order. And so cluster one got plotted first, and it's like very much in the middle. And then cluster two in red, its mean is very, very similar to cluster ones mean, right? So if you look at cluster one and cluster two, like as far as the X2 component, they're like almost exactly the same, 0.0255 versus 0.0254. And then for the X1, it's 0.086 versus 0.037. So this one is just ever so slightly to the left of it, and it gets plotted on top. So it almost completely covers the centroid for cluster one here. Okay, and then cluster three in green is over here. And that's just the result of just kind of randomness. And then we say, all right, which centroid, we're going to reassign all of the points to the nearest centroid. And so when we do this, pretty much everything over here on the right-hand side, when you measure the distance, it's going to say, well, green is the closest of the 3 points, okay? And then everything on the left, you say, hey, which centroid's the closest? It's going to say, okay, the red one is the closest one. And there's really only a few points where it's going to select black, cluster one, as the nearest centroid. Maybe these points? I don't know. Just a few of them. So when we reassign the points, this is what ends up happening. All of these get assigned to green. All of these get assigned to red. And then, yeah, this one is just kind of, there's just a very few points where it says, okay, cluster one in black has the closest centroid versus red versus green. Okay. And so just a few get assigned to cluster one, but that's okay. Um, there is a possibility that after you do reassignment, like you start off with three clusters and then after reassignment, there's only two. That could happen. It's rare. And then in that case, you end up just searching for two clusters. And then so you probably just have to redo the random assignment in the beginning to make sure you find three clusters. Anyway, this is what we have after reassigning the points to the nearest centroid. So then we recalculate the centroid. We say, okay, what is the center of all of the points assigned to green? What's the center of all of the points assigned to red? What's the center of all of the points assigned to black? And this is what you have. So the center of all the green points, center of all the red points, center of all the black points right here. And then we recalculate centroids. And so now, as far as these points over here on the right, yes, green is still the closest centroid. Okay, but now we can probably draw um, almost like a line. Can I draw a line? Like kind of looking at the line that connects this, we would say like, okay, what is halfway through? And probably drawing a line kind of perpendicular there. I would draw some kind of split, and I would say these points are closer to this centroid, and these points are going to be closer to this centroid. Okay, and doing something kind of similar here, looking kind of perpendicular. I don't know. I'm just kind of eyeballing this. And this would be kind of my guess as far as what's going to get reassigned. And we're going to say these points are probably closer to the center centroid, these ones over there. All right, and then let's see how I did. So this was my guess. Yeah, pretty good, I think. Um, and so after reassigning the points, this is what we have. And then now we say, okay, what is the center of all of these points in green? What are the center of all of these points in black? What are the center of all of these points in red? And so we recalculate the centroids. Okay, so you go from there to there, right? So this is what you had. You recalculate the centroids. You're going to reassign points to the nearest cluster. You get that. And then you recalculate the centroids. And then you do the same thing. You reassign points to the nearest cluster. So probably looking between here and here. This one's a little bit tougher. I'm going to guess something around there. Okay. And then I don't know if I had to do this right here. That would be my guess. I don't know. Okay, so we reassign points. All right, so going from there to there. Yeah, kind of. All right, and then recalculate centroids, reassign points. So you just kind of go back and forth. So recalculate centroids, reassign points, reassign points, recalculate centroids, reassign points, recalculate, reassign. And then so here between, I'm flipping back 35 to 36. Really, there were two reassignments, this point and this point right here. Um, how do I, so I think this point gets reassigned and this point. Um, and then so there is a reassignment there. And then we recalculate. So just ever so slight shifting between 36 and 37. And then here at this point, there's no reassignment. No points get reassigned. So we're going to say it has converged. Okay, so at this point, when there's no changes, it has converged. We can kind of compare it to the original. All right, so this is normally something you can't do because you don't actually know the generating data, and they're coming in completely unlabeled. So in this case, we got pretty close. There are a couple things that are different, like this one and this one and this one. I think those ones changed. But other than that, um, I think it identified the clusters, quite well, right? And I would say these ones are kind of outliers for each of their respective original classes. So we say this clustering algorithm seems to have performed quite well. And that's what we have there. Okay. You can run k-means clustering in R. There's just a function called k-means, and and it works quickly. And here it has identified three clusters. And I think this is almost exactly the same. So looking at this and this, yeah. Again, what it has done, it has just arbitrarily called this one cluster 2 in red, and this one's cluster 3 in green, and this one's cluster 1 in black in the center. But again, the labels are not, it's fine that the labels get switched up because, again, our data comes in unlabeled and we're just looking for structure. And we're not saying, we don't have answers. We're not saying like this is, um, category A and category B and category C. We just say, hey, search for three clusters, and it does correctly identify the clusters, but the labels have been switched. But that's fine. Okay. Um, with k-means, there's a few different options. I mean, one of them is just how many clusters you're going to search for. All right. And so here we said we're searching for three clusters. Okay. We just call k-means on our data frame, our matrix here, and we just say three. Now, this is assuming this has already been normalized. Okay. Um, and it finds it there. Okay. And you can kind of think of k-means as an optimization problem in that it's seeking to partition the observations into k different sets so that the within group sum of squares is minimized. And you can think of the within group sum of squares as being calculated as the kind of sum of squares distances from each point to the centroid of the group it's assigned to versus the total sum of squares being the distances to the kind of grand centroid. Okay, so if I go back to say this point, this slide, what you're doing is you're calculating. I would have to draw like some kind of grand grand centroid. Like what is the centroid of all of the points? Okay, and so um, I don't know, maybe the center of all of the points is right here. Okay. And what we're doing is we're comparing, um, kind of like doing ANOVA. You're saying when you look at each of these points, you're calculating, what's the distance from each point to its own centroid. All right. And so this would be like the within group sum of squares. So we're looking at each point, all of these points, you're just calculating the distance to its own respective centroid versus what is the distance to the grand centroid. Okay. And so you can see the distance to the grand centroid is going to be much greater, right? So comparing distances from each point to its own centroid versus each point to the center of everything. So this would be our grand centroid in the center in blue versus, how far is each point from its own group mean versus the grand mean. Okay. And and so what trying to do is we're trying to minimize the within sum of squares. Okay. Versus the between sum of squares. So think of it as kind of an ANOVA problem where you're taking that total variance and you're splitting it into two different sources, between group variance and then within group variance, your residual variance. And the residual or the within sum of squares is basically the distance from each point to its own centroid. And then the between is, how different is the centroid from the grand mean. And then the total is each point to the grand mean there. Okay. And so this is revealed when you look at the results of the k-means function. You have this part right here that calculates the within the within cluster and versus and you get kind of this between cluster sum of squares divided by the total sum of squares. Okay, and so this is almost like an R squared value. 86.2% is almost like the R squared value. And so um, you get the within cluster, and we're trying to minimize the within cluster sum of squares here. And you have you know, these different things that you can kind of measure out. So you have the total within sum of squares, you have the between sum of squares, um, you know, the within sum of squares itself. So if you do the total within sum of squares divided by the total sum of squares, um, you would get, I'm sorry, the between sum of squares divided by the total sum of squares. That's kind of your R squared value. And you can kind of find all of these within sum of squares themselves directly, okay, as components within the output of k-means. So if you look at this, here our total sum of squares is 4463. And then the within sum of squares, we have 226, 198, 193. Oops. So here you get the not rounded off. You see the 226, 198, 193 right there. And then and so if you add these up, the total within sum of squares, 226 plus 188 plus 183 will add up to 617, which leaves, 617 plus 3846 will add up to 4463. And so you can get your R squared value, right? So 617 plus 3846 will add up to 4463. And so if you do 3846 divided by 4463, you'll get around 86%. And that's our kind of our R squared value here. Okay. Now, with k-means, you can search for like the wrong number of clusters. And so if you say, hey, search for just two clusters, it will do it. And this will be the results that you get. Okay, so it just says, all right, I've identified two clusters. Here we have cluster one over here on the right, cluster two over here on the left. And you can calculate the between sum of squares. Okay. And so, whoops, that's with k, I'm sorry, with k equal to 2, our between sum of squares divided by total sum of squares is around 69.7. All right, so comparing that to 86.2. So think of it as an R squared value. We can see, all right, k equal to 2 doesn't explain as much variance. Okay. You can also try, say, k equal to 4. Okay. And with k equal to 4, your variance goes up 88.3. Okay. I mean, not variance, kind of your R squared value, that we can think of it as R squared, goes up to this. We can also see our four clusters. We have this 54, 56, 93, 97. We have these different clusters here. Okay. So I identified this cluster, and it kind of split the one in the middle into two things. Now, the thing is when you have the quote wrong number of clusters, and I mean, this could happen even with the quote right amount of clusters, because you are randomly initializing, you're initially assigning points to different clusters in the beginning, you can end up with very different results. And so if I rerun k equal to 4, here I just tried a different random set seed. I did set seed 2 instead. And my clusters ended up like this. Okay. So we have a cluster on the right, cluster on the left, but the one in the middle kind of got split vertically. Okay. So looking at this result versus this result, we can see we ended up with different results, right? And so this this we had between sum of scores of 88. I'm sorry, the R squared of 88%. Over here was 88.3. So we're getting, different values. Here's another one. Um, and it split this one. And and so you can end up kind of just getting these different results. And the question is, well, how do you know how many clusters to search for? Okay. And this is um, almost an impossible task. How many clusters to search for is very challenging, sometimes impossible. Um, and the bottom line is you can always kind of segment your data into smaller subgroups that share something in common. And every time you segment your data into smaller subgroups, um, your kind of R squared value will go up a little bit. Okay. And it's hard. It, just an example of how difficult this question is. You can imagine if you are running the census, and one of the variables that you might collect information about is, demographic, race and ethnicity variable. And how many races and ethnicities should you search for? And this is a really difficult question, okay? If you go back several decades, okay, the census form would have really only had kind of two races or two options, either white versus non-white, okay? And as time has progressed, we have different options. You can have white, um, black or of African descent. You can have Asian. There's a variable for Hispanic, or there's uh, not Hispanic, non-white. There's all kinds of different things, and then I am Asian, but among Asian, you can further dis split that into, you know, different different kinds of Asian. So there's, East Asian, South Asian, Southeast Asian, Central Asian, um, and then, say among East Asian, that can be further split into, Chinese or Japanese or Korean. Among Chinese, that could get further split into, different kind of, uh, ethnic groups. And so, how many, at what point do you say, okay, I think this is enough? All right. And again, if you gave that task of creating different, how many subgroups or clusters should you form, probably different people will come up with different answers. And so this is a really kind of challenging thing. So choosing how many clusters to search for is really hard. You can always make the argument and say we could have more clusters and it will improve performance. But then at what point do you have too many or something? One option you can do is you can, and not that this is the answer, but you can, run it a whole bunch of times. Okay. So if it's kind of like if you gave this assignment of like, all right, figure out how many demographic categories to have. And if you gave it to a whole bunch of people and then, everybody comes up with slightly different things, but overall a bunch of people kind of agree on the same things, you might say like, all right, we have pretty good agreement among a bunch of people. So therefore we feel this this one that kind of shows up a lot is a reasonable choice to go with. Okay. And you can kind of do something like that. If you have the computational resources to run k-means clustering multiple times, okay, you run it multiple times, and if multiple runs converge to the same cluster assignments, um, then as you're looking from one run to another, the within group sum of squares will have no variation or kind of very little variation, right? On the other hand, if the multiple runs don't agree and you're getting like wildly different results every single time, you're going to have a lot of kind of variation on these within group sum of squares, okay? So, here I'm just demonstrating this and I'm going to try out this is a double loop, and I'm going to run k-means clustering 20 times, okay, for different values of k. I'm going to try k equal to 2, k equal to 3, k equal, up to k equal to 10 on our data set, okay? And for each of these things, I'm going to look at the within sum of squares value here. So when I ran it 20 times with k equal to 2, what we see is that when you choose k equal to 2, you get the exact same within sum of squares all 20 times. Okay. Here, when I chose k equal to 3, I got the exact same within sum of squares every single time. Okay. But then looking at towards the later ones, when I have k equal to 9, each time I run it, I'm getting different within sum of squares. Okay. Sometimes the within sum of squares is as high as 243. Other times it's lower to 254. Okay. Here, when I did k equal to 10, what happened here? With k equal to 10, I'm getting, again, very different results. 306, sometimes as high as that, sometimes much lower to 232 or 230, sometimes somewhere in between. Okay. And so I can just kind of create what is the average within sum of squares for each of these different k's? Okay, and then what's the standard deviation? So with k equal to 2 and k equal to 3, there's no standard deviation because we got the exact same value every single time, 616.887. Okay, and then when I have k equal to 4, we do have some variance. K equal to 5, we have some variance. So on average, it's 534 with some discrepancy, with k equal to 10, 250. I guess the average is 258. Okay. And we can see sometimes it's much lower, like 230, sometimes higher at like 306. And so the standard deviation between those numbers, 24.2. So just looking at kind of how much the within sum of squares changes from run to run. Here's kind of a plot. So with k equal to 2 and 3, there's no variation at all. And I got box plot, and we can see, there's, a little bit of variation with each of these things. And so, how do you decide which K to search for? We can say, well, we had no variation, so K equal to 3 is probably the best. But, one could argue any of these things are okay. And as we kind of increase the number of clusters, we do find, our within sum of squares goes down, basically means our R squared is going up. Um, I don't know. It's a tough question. Okay. Searching for K. It's like, how many product categories should you have, um, on your website? And do you just kind of group everything together, foods versus non-foods, or do among the foods, do you split them into, I don't know, produce and dairy and I don't know, different categories, right? Um, and yeah, a lot depends on kind of your infrastructure and things like that. So, anyway, I said big drops when we go from 2 to 3. After k equal to 3, sum of squares improves, but not as dramatically. So, who knows? Okay. Um, so that's k-means clustering. We can also run k-means clustering using kernel functions. And so we'll take a look at this, okay? So we introduced kernel functions when we were doing support vector machines. And we said, these kernel functions can transform our data into kind of a higher dimensional space. And so we saw the data go from two-dimensional data get transformed into three-dimensional data. And in 3 dimensions, we could draw a linear boundary, a linear hyperplane, basically a plane that is able to separate our data. And that was useful when we did support vector machines. Um, when we run it here, okay, uh, we'll use the cluster kernel function during our clustering, okay, and we run it. Oh, so this is just a review of the k-means clustering algorithm. Oh, and this is just another slide to kind of another example. So here I have 3 clusters, and we can search for 3 of these things, and we have red, green, and black, and these are the ones that get assigned. And apparently, which points that get assigned to green, there's only a few here, but um, when you kind of run each of these things, eventually it does reach convergence, okay? And it finds kind of 3 clusters there. All right, so we introduced these kernel functions and said, basically we were applying some kind of transformation function phi that perhaps transforms our data from 2D into 3D or 2D into a higher dimensional space, like the radial basis function transforms it into infinite dimensions. Okay. And then we take the inner product, and that will be our measure for our kernel distance. Okay. Or I guess our kernel function measure here. So we have this. If you don't transform it, okay, with a linear kernel, the phi function is the identity function, and so you can just do XA transpose XB. But then you have these other functions, like here we're going from 2D. So if we apply this phi transformation function that goes from 2D to 3D, um, we can go from x1 and x2 into a three-dimensional point, x1, x2, and then our third coordinate would be x1 squared plus x2 squared. And the equivalent kernel function would be, xa dot xb plus the norm of xa squared and the norm of xb squared, right? And this will give us the same results. Other examples. Here's another kernel function. This is a polynomial kernel, and so if you have c equal to 0 and gamma equal to 2 on this case, the equivalent transformation function looks like this, okay? And you go from x1, x2 to x1 squared to x2 squared and root x1 times x2. And if you kind of if you apply that to xa and xb, so you have xa1 squared and a2 squared and so on and so forth, and you say, okay, what's the dot product between these two things? This would end up being xa1 xb1 squared plus xa2 xb2 squared plus 2 XA1, XA2, XB1, XB2. And this is equivalent to kind of taking the product of XA transpose XB, which would give you XA1, XB1, and XA2 and XB2, and then taking this whole thing and squaring it, right? So this is just kind of if you take basically this plus this quantity squared, you just get, through algebra, you get this big thing, right? And so the equivalent kernel function is XA transpose XB transpose quantity squared, okay? And that's this kernel function, and this is the equivalent transformation function. And there's different examples of these kernel functions and their equivalent transformations, okay? And so that's the example of a polynomial kernel. And again, the radial basis function kernel, where you take e raised to some, the difference between xa and xb, the equivalent transformation function exists in infinite dimensions, okay? So, we would not be able to write this out because this one is 3 dimensions and we can write it out, but with infinite dimensions, we would not be able to write it out. But that's okay. You don't need to know the exact transformation function. You can just kind of work with this inner product, okay? And so all of these kernel functions are inner products of vectors after they've been transformed, but you don't need to think of the transformation itself. We can just kind of take this inner product, okay, and just substitute in anytime we see XA transpose XB, we could substitute the kernel function there, okay? And this will basically apply the kernel function and do the equivalent kind of math in this transformed space. So what we're going to try to do is we are going to try to re-express this idea of what is the distance from each point to the centroid. We're going to try to express it as an inner product, okay? And then if we can express it as an inner product, we can then replace these things with the kernel function. And then it would be, what is the distance from each point to the centroid, but in this transformed space. So, so what we want to do is we want to express, okay, how do we get the Euclidean distance from each point to its respective centroid? And then once we have that expressed as inner products, we're going to replace all of those inner products with the kernel function. And then it will be, what is the distance from each point to the centroid, but in the transformed space. So, right now, the way we calculate the distance from each point to the centroid is we say, basically, what is the difference between each point and the centroid? And you can think of as the squared distance, you taking the difference between, x1 and the mean and x2 and the mean in dimension 2, and you're squaring that distance and you're adding them up. And so, the squared Euclidean distance we can find by doing x minus mu transpose times x minus mu, okay? And then that centroid itself, mu, is the product of basically our indicator variable z times x, okay? All right, so z is ones and zeros, times x, and then we're going to kind of add them up across and then divide by how many points we have in cluster K, right? So we're just taking the mean of all of the points that belong to cluster K. So this is a crazy mess here, but we might say, okay, if I take this definition of what is the centroid, okay, and replace the mu with this thing, so I just have a bunch of x's, okay, we can expand this out, right? I'm going to have a different letter subscript here. We're summing over m, and over here we're summing over r to kind of indicate that we're we're summing over different letters. And so basically, we are going to uh, calculate distances to the centroids by kind of taking a product of comparing every kind of point with every other point in our data set. Okay. So anyway, this is a big mess here. And um, I won't bore you with all of this, but basically you can kind of multiply each of these things and then so you'll have this double summation. Even though we're summing over M over here and summing over R over here, because we're working through the entire data set, okay, this entire thing is going to be exactly equal to this entire thing. So summing over M here, we're looking through all of the data points here, and we're summing over R here, and we're going to work through all of the data points here. This summation and this summation will be exactly the same. So I can just kind of combine them, and I just arbitrarily chose the letter M here. But then over here, we are going to compare every point versus every other point. So we're going to compare every point x sub m to every other point in our data set x sub r. So we're going to compare point 1 to point 1, point 1 to point 2, point 1 to point 3, point 1 to point 4, and then, point 2 to point 1, and point 2 to point 2, and point 2 to point 3, and point 2 to point 4, and so on and so forth. And we would go through kind of every single combination and, take into account basically our which points belong to cluster one and cluster two and so on and so forth. Okay, so anyway, this has the goal of this was to find a way to calculate our distance metrics. Okay, this is the squared Euclidean distance from x to the centroid. We've now expressed it in a whole bunch of just inner products of x. Okay. And what we're going to do is we're going to replace all of these inner products here with kernel functions. So this is how we can measure the distance from each point x to the different clusters, centroids, and then we can apply the kernel function and replace anytime we see an x transpose x, okay, we can replace it with the equivalent kernel function. So here I can do kernel function of between xn and xn. Here I'm looking at xm transpose xn, and we will have the kernel function between xm and xn. And then here we're looking at xm transpose xr, and I'll have the kernel function xm xr. Okay. And so this is, what is the distance between point n to the centroid of cluster K? And it depends on, point M's membership to cluster K, and then the membership of, all of these other points are, do they belong to K or not? So we're looking at all of the other points in our data set, and we're asking, what is the kernel distance between, um, n, n and the centroid of K, okay? Now, the crazy thing is that we are able to calculate the distance to the centroid without actually knowing where the centroid is. Okay. That's kind of the crazy thing. I mean, that falls out from this result here. So before, how do you calculate the distance from a point to the centroid is you need to know the point, you need to know the location of the centroid, and you say, how different is my point from the centroid? Okay. But when we expand this out, we don't have a definition of the centroid anymore. We just have all of these kind of cross products. Now, the definition of the centroid is somewhere, is kind of, or the actual location of the centroid is no longer needed, but we are still going to get the distance because we are going to look at kind of every point and compare it to every other point here. Okay, so it's a little bit of a you know, in my opinion, it's kind of surprising that we don't actually need to figure out the centroid in our higher dimensional space. Okay, we just calculate all of these kind of cross products between x and every other point here, and then it works. So when we do kernelized k-means clustering, okay, we run the same kind of a very similar algorithm. Okay, so we just kind of randomly assign points to each of our clusters, but then there's no recalculation of centroids. We just reassign points based on associating the values to the nearest centroid using the kernelized distance. So I guess without recalculating centroids, you just recalculate the distances. So you recalculate your distances, reassign the points. Recalculate distances, reassign the points. And you recalculate the distances to the nearest centroid without actually having to figure out the centroid itself. Um, and it works. Okay. So here I'm going to do a very kind of simple data set and show how this is going to run here. And so I want to illustrate this. Uh, where's my okay? So let me. So here, my data set, I've got 8 points. I have a point at negative two, and 2 comma 2. I basically have these 4 points on the outer ring and then 4 points near the center here. Okay. And if we use Euclidean distance to cluster these, um, well, so just visually, I would, you know, my own brain, I would say, okay, these 4 points in the center belong in a cluster. And then even though these 4 points on the outside are different from each other, we would put them in a cluster together. Now, using Euclidean distance only, we would never put Euclidean distance would never put this point at 2 comma 2 in the same cluster as this point at 2 negative 2 because Euclidean distance says these are as different as they can possibly be. The distance between this and this is maximum. So they are very different, and Euclidean distance would never put them in the same cluster. So in order to kind of put them into the same cluster, we can't just use Euclidean distance in this two-dimensional space. We're going to transform our data into a higher dimensional space. And then in this higher dimensional space, we can then use Euclidean distance. And when we do that, these 4 points in the higher dimensional space will be closer to each other. So we are going to use this transformation of having x1, x2, and then x1 squared plus x2 squared. And so we're going to apply that transformation. And so, our the outer points are located at 2 comma 2 and, negative 2 comma negative 2. But adding the third coordinate of x1 squared plus x2 squared, you know, the third coordinate is going to be 8 for all of these things. So 2 comma 2 gets put up to 8. 2 comma negative 2 comma negative 2 gets, x1 squared plus x2 squared gets put up to 8. All right. Whereas the 4 points in the middle, they were at, zero point 0.1, negative zero point 0.1, and so on and so forth. And they're, when you bring in x1 squared, x2 squared, they all get put at 0.02. And so I'm going to do a 3D plot of this. Here we randomly assign points to just two of the clusters. So point 1, 4, and 8 get assigned to cluster 1. Points 2, 3, 5, 6, and 7 get a point assigned to cluster 2. And so this is kind of what it looks like. Let me see if I can plot this here. Um, all right, so this is a representation of our points. Okay, so I don't know if you guys can see this. So we have the 4 points at 2 comma 2 and 2 uh, what is this? This top one is at negative 2 comma 2. This one is negative 2 comma 2. I guess this is negative 2 negative 2 2 comma 2 2 comma negative 2, and then you have these different points. We have red and blue here, and so you can kind of see this. And so when you ask what is the mean of the points in red, the mean of our points in red, we have this point, this point, this point, and then these 2 points in the center. The mean of the 5 points in red is right here. What is the mean of the 3 points in blue? That mean is right there. Vertically, what is the mean of the 5 points in red? We have, 3 on the ceiling and 2 on the floor, and so the mean is kind of pulled up in the direction of the ceiling. And then as far as the ones in blue, we have 1 point on the ceiling and 2 on the floor, and so the mean is kind of down here. And so, the diagram looks something like this. And here, I guess this plot, it looks kind of like this, right? It's kind of hard to see when it's flattened down, but then when you can kind of plot all of this, it looks like this. So anyway, the mean of the points in blue is at negative 0.67, positive 0.67, and 2.68. And the mean of the points in red are at zero point 0.4, comma, negative zero point 0.4, and 4.88, or 4.8. And so doing that, we will calculate, all right, what is the distance from each point to each of the centroids? All right, so here we're working in this transformed space. So this is what we have, and we say, okay, what is the distance from each point to each of the centroids? And we can calculate that. And working through that. So the coordinates of centroid A is this, and what is the distance between centroid A and the first point is going to be, that's, this minus this squared, and that distance is going to be 7.984. Okay, and we can do this for all of the other uh, points. So we can say, all right, distance to centroid A, 7.984. Versus what is the square distance to centroid B? All right, so looking at point 1 to the red one. Okay, so this distance is going to be 7. This square distance is 7.984, and the distance to this point is going to be 23.26. And we do the same thing, this is all of these points, the distance to this centroid down here is, on the order of around 8. So the distance from here to here is 7.98, 8.25, 7.7, 7.98. Okay. And what's the distance from all of these points to here? And they're all on the order of 23. Okay. 23.2, 23.1, 23.46. Okay. Meanwhile, what's the distance from the points on the ceiling to each of these things? All right. And those, the points on the ceiling to the blue centroid is are on, 37, 42, 37, 31.85. Okay. So I think these 2 points both have a distance of 37.191. How far is it to this one? This one is much closer, distance of around 18.5. Okay. And so doing that, if we reassign our points, okay, and we recalculate the centroids, what's going to happen is the 4 points on the ceiling will get assigned to one cluster in red, and the centroid is going to end up there. And the points on the floor get assigned to the blue cluster in the bottom, and the centroid is going to be in the center of those 4 points down there. So that's what ends up happening. And that's this plot right here. Okay. So this, it's a little bit hard to see. Um, but this is, I think, this image right here where, the 4 points are on the top and then the centroid is up there. And then you have the 4 points down here and they're in blue and the centroid is down there. Okay. So that's what ends up happening there. Okay. Um, the and then you can recalculate your distances to each centroid and so the 4 points on the floor to the centroid in the center, very small distance. The 4 points at the top, their distance to their centroid is now 8. Square distance to the centroid is now 8. And this was done by transforming it into that three-dimensional space. Okay, so we were able to kind of see these plots and say, okay, well, these are where our points are, and we can calculate these distances in the three-dimensional space. But with the kernel functions, we don't actually need to figure out the locations of the centroids. Okay, so we don't actually have to transform our data into 3D. We can use that kind of crazy summation formula from, back on these slides, basically using this result. And we can say, all right, we're able to calculate our distances using the kernel functions directly without actually having to figure out these centroids. Okay, so pay attention to these distance numbers. So this first one, we said, what's the distance from point 1 to centroid A? It was 7.984 and 8.251 for the next point. And we calculated the distances to those centroids. Okay. But we did it by kind of finding the actual coordinates of centroid A. And we said, what's the difference? And we squared those differences and we added them up, right? We did 0.67, minus 0.1, or zero point 0.1 minus negative 0.67. We got positive 0.76, and you squared that and you add them up. So 0.76 squared is 0.58, negative 0.56 squared is 0.32, and negative 2.66 squared is 7.07. You add them up and you get 7.98. Okay, so we did the squared distance to centroid A by kind of taking these differences to the centroid and adding them up. We're going to end up with this same result of 7.98 without actually having to transform any of our numbers. Okay, we're going to leave it in this form of 0.1 and negative 0.1 and 2 and negative 0.2. We have these assignments. Okay, and it feels kind of like a lot of work here, but we are going to just calculate this distance equation. Okay, so we have to kind of compare every kind of M to every kind of R. Okay, so I'm going to kind of get this kernel, this matrix of kernel distances between every point M and R. Okay, and that's found by going to do xm dot xr. Okay, so xm matrix multiplied by xr. And then we're going to take the norm of xm squared times the norm of xr squared. Okay, so I'm going to basically find this matrix for every single thing here. And so I have kind of this big kind of kernel matrix where we took all 8 of our points and we have some kind of measure between each of these things. And this will come into play as far as getting this double summation here. Okay, so this is just what is the kernel value between xm and xr for every combination of m and r. Okay, and so when we want to calculate this double summation, I'm going to look at this vector for z, okay, which is ones and zeros. And so we're going to basically go through all values of m, r 1 through n, and then we'll do it for m 1 through n. And I'm going to just kind of calculate basically for some cluster A, okay? For cluster A, we're going to say, all right, what is it a 1 or 0? Times for cluster A, is it a 1 or 0? And we're going to multiply by that kernel value. And we're going to just kind of keep a running sum. And when we do the double summation, we get 72.646. You can also, a shortcut to this is you can take that entire kernelized matrix and then do a multiply that vector ZA against itself and do the same thing, and you'll get the same result. But anyway, this is the double summation. We get this. And then we'll do the same thing to calculate all of these other things. So for, every kind of point here, we'll look at Kn, the kernelized distance here. We'll look at the sum across these values here. So we're summing up across M. So we can just take that column N here. And you'll notice all of these distances, when we do this, we can get the distance from each point to the center, the square distance to the center of cluster A, and we get, 7.984, 8.251, 7.7184. It's not slide 35, but like if I go back, where did they go? Okay, so yeah, slide, I guess, 93, when we say, all right, we calculated the distance to the centroid of cluster A. We have 7.984, 8.251, 7.718, all the way down to 31.858. And we have those values here, 7.984, 8.251, 7.718, all the way up to 31.858. Okay, so using this thing without actually transforming our data into the higher dimensional three-dimensional space, we are able to get the same distance metrics from each point to the centroid of cluster A, right? And it feels almost like magic, okay? But we just have an alternate way of calculating those distances by using this kernel function. Okay, so the kernel function is working in that, is giving us values back from that transformed space without actually requiring us to transform the data. So we can do the same thing and calculate what is the distances to the centroid of cluster B, okay, in that transformed space. So, working on the double summation for all of the assignments to cluster B, Z underscore B, and then working through the, distances for each of these things, okay? We can get all those things in there. And again, these things match the values to the distances on slide. This is actually 93, slide 93, okay? And so comparing these things, we can say, all right, let's look at which distance is smaller. So cluster one, point one will get assigned to cluster A, and points 1 through 4, their distances to cluster A are much smaller, and points 5 through 8, the distances to cluster B is much smaller. So everything would get assigned to cluster A up here, and then these 4 points would get assigned to cluster B. And so we would end up with the same results there. Okay, so putting everything all together on the same kind of slide here at this next iteration, we can recalculate what are the distances to centroid A here, and what are the distances to centroid B here, and we get the same results that we did earlier. So that's how doing clustering works by using a kernelized function. Okay. And so again, we can work in, very high dimensional spaces, like for example, the radial basis function transforms it into infinite dimensions. And if you said, well, I want to calculate the centroid in this transformed space, you would not be able to do it because that centroid has infinitely many coordinates. So, I mean, you might be able to get an approximation where you say, oh, well, we'll just keep the first 30 coordinates, but still, you don't have to do that. You can just kind of work with the kernel function. Okay, so we have some way of calculating the kernel function here. All right, so here we said the kernel function is for the um, three-dimensional kernel basically are x1, x2, x1 plus x2 squared, x1 squared plus x2 squared. the equivalent kernel function is this, we can apply the same, but using like a radial basis function kernel, and we'll get that. And so this is just a made up example where I'm going to have two clusters of points. Okay. I'm going to have a bunch of points in the center, and I've got a bunch of points on this outer ring. And if we just did k-means clustering, using Euclidean distance, it would never put the points at the top in the same cluster as the points on the bottom because those distances are far. Okay, so here's like the result of k-means clustering. It puts these points up here in one cluster, and it says, okay, all of these points down here on the second half, on the lower half, they belong to a different cluster. Okay, and this is probably not how we would cluster them like ourselves. We would probably say the points in the middle belong to one cluster, and then the points in the outer ring belong to a different cluster. But again, k-means clustering would not be able to do that because according to Euclidean distance, the points, at the top are very different from the points at the bottom. But what we might try to do is we might use a kernelized k-means clustering. And again, this is going to project our data into a higher dimensional space and then reassign our points. Okay. And so here, so I've run it, and our kernel function here is going to be e raised to the negative gamma, and we take basically the distance between xm and xr, and we're going to kind of take that difference and square it and add them up. Okay. And so this is our kernelized kernel function for the radial basis function or Gaussian kernel. Okay. And so using this, I can basically run through the same code that I had earlier when we did just the toy example with 8 data points, but now it's just a bigger thing with more data points. And so I initially start off with just random assignments. Some points are assigned to cluster 1 and some are assigned to cluster 2 and shown in black and red. And then uh, we say, all right, calculate the distance to each centroid based on the current assignments. And again, we don't know the actual location of the centroid, but we are able to get the distance to the centroid. And so we redo these assignments. And so we calculated the double summation for centroid A, double summation for centroid B. We get the distances to centroid A and the distances to centroid B. And this is just basically the code from the previous slides. And we say, go ahead and calculate um, which centroid is smaller. Okay, distances to A versus distances to B, which one is smaller? And that's going to be our new assignment here. Okay. And so after one iteration, this is the new assignment. Some get assigned to red and some get assigned to black. We don't fully understand what's going on here. Again, the data has been projected into this higher dimensional space, and apparently, um, in this higher dimensional space, some of these points are closer and some of these other points are closer. Okay. By the next iteration, this is what we have. And so all of these points have been clustered together, and we have some of these points in the center belong to one cluster and some belong to the other cluster. And we're just gonna, we keep getting some reassignments, so we'll redo it. And here's uh, after another iteration, and here's another iteration after some reassignments. And at the next iteration, we see no points get reassigned, so we would say it has converged. Okay. What's happening in the higher dimensional space? I don't know. Okay. But that's okay. We have a way to project the data into this higher dimensional space. We have a way to calculate the distances to the centroids, and based on those distances, we reassign them. Okay. So here we're converged, and that's that. And so I wrote a few extra uh, couple extra slides that said, how does this thing work? Because again, I had when I was learning this and teaching it myself for the first time, I really struggled with the idea of like, how are we calculating distances to a centroid if we don't know where the centroid is? Because it just felt strange. Like, how do we calculate the distance to the centroid if we don't even know where it is? Okay, so so I wrote is the actual location of the centroid is left undefined because that requires the use of that transformation function. But instead, the distance, from a point to the centroid is expressed as an inner product that can be calculated. Okay, and we can think of these inner products as some, measure of similarity, even if it's not really directly that, okay? And what we're able to do is we're able to kind of compare each point to every other point in the data, and we're still able to measure the distance from each point is to the centroid, okay? And this allows us to work with the result of transformations without ever running the transformation function itself, okay? Um, and my analogy is kind of like friend groups. All right. So imagine trying to kind of form friend groups in a large room of people. And how do people end up kind of clustering themselves into these little cliques, right? And the thing is that no one is going to try to match themselves to some theoretic perfect friend or the central idea of a friend group. Okay, so you might have these different cliques and these different friend groups, but what is like what's the centroid of that friend group? That doesn't quite exist, right? It's kind of like uh because you have these things that define different friend groups, right? Similar humor or political views or maybe similar interests, like you like sci-fi or something. Okay. And so instead, uh, people look at, so it's not like each group has uh, a centroid, like a defined centroid, but instead the person looks at the other people in that group, okay, and uh, by looking at the other members of those group, you can kind of think of that as like a pairwise similarity, right? You say, all right, I get along with this person, I get along with that person, I don't really get along with that other person or something, right? And so you have this kind of this measure of quote pairwise similarity, looking at every other thing. And then by knowing who belongs to which group and measuring your own kind of similarity with other things, you can get an effect and say like, okay, I'm similar to the other members of this group, even if each group doesn't actually have a centroid defined. Okay. So I wrote, to decide which group to join, a person doesn't compare themselves to the abstract ideal of the centroid, but instead they kind of ask like, which of these groups as a whole do I feel kind of the most collectively similar with, right? Looking at, the pairwise similarities, okay? And so you're effectively averaging their similarity scores with everyone in a potential group and choosing the one that kind of fits the best, right? And so, our people, the data points that we have, you can kind of think of those people, and then this the reason for friendship of why the group exists is kind of like this transformation function that we don't really get to see or know, okay? But we have this kernel function that gives a measure of like a pairwise similarity between each of the points, and then you can kind of get a measure from each individual to the, I don't know, the cluster centroid, okay? By knowing the membership, right? By knowing who belongs to each kind of friend group there, okay? And so that's kind of the kernel trick, and we can kind of group similar observations together. All right, so that is our lecture on clustering, and we'll look at a few more kind of um, uh, unsupervised learning. Actually, I've got the EM algorithm and I've got principal components analysis. So we've got that, and that will kind of wrap up all of the different topics that we have. Week 6, I think on the first lecture, week 6, I just kind of have some random things that are for fun. Um, I'll talk a little bit about the final exam because that's going to be a week from Thursday. So that's coming up fairly quickly. So I'll talk about that on Thursday as well. All right. With that, have a good rest of your day. Oh, sorry, I don't have a lecture view quiz for today, so thanks for being here. But yeah, I don't have a view quiz set up for today's lecture. All right. All right. We'll see you guys later then.